In this video, I'm going to show you how to use the PID-controlled one mass, one spring module in the Control Theory Virtual Lab. Firstly, I'll show you how to properly set up the downloaded folder. When the folder is downloaded, all the necessary files are included. The folder consists of the Control Lab SLX file, 13 step files, and 2 data file mat files. For the module to work correctly and load all the necessary solids, all the step files must be on your MATLAB path. This is achieved by either having all the files in the same folder and opening it as your current folder, or by manually adding the files or separate folder those files are in to the MATLAB path. If the files are not on your MATLAB path, this error will appear when you try to run or update the simulation. Each module uses a PID controller to control the position or path of a specified mass. To select the one mass one spring module, click its blue title, then double-click the now highlighted box. In this window, there are buttons that control the simulation. Open the PID controller menu and open the position plot. The Update Model button opens and updates the Mechanics Explorer with any new applied changes. The Start Simulation button updates and runs the simulation, and the Stop Simulation button can stop the simulation before it finishes, but all the data simulated until that point is still available. The one mass, one spring module consists of 2 separate but equal systems, meaning any changes made to parameters in the Variables tab, the Free Response tab, and the Forced Response tab are applied to both systems. The top system has a PID-controlled mass, meaning you can choose a desired path or constant position for the mass to follow. The bottom system has no PID control, so that the position data can be compared. The Open Scope Plot button opens a window of a graph with position of the mass in centimeters versus the simulation time. The yellow line is the position of the non-PID controlled system on the bottom. The red line is the desired position chosen. The blue line is the simulated position of the PID controlled system on top. You can change variables like mass and spring constant in the Variables tab, input an initial displacement in the Free Response tab, and set a step or harmonic force in the Forced Response tab. Also in the Forced Response tab, you can set the initial displacement to 0 by checking this box. This disables the initial displacement slider. Likewise, in the Free Response tab, you can disable the force applied to the mass by checking the 0 forces box. In the PID Desired Position tab, you can choose either a harmonic or square path, or a constant position the mass should follow, despite any displacement or force applied. The Open PID Controller button opens the PID Controller window where you can change the proportional, integral, and derivative constants. Make sure that Select Tuning Method is set to Transfer Function Based. You can either change the constants manually, or you can use the Tune button to let MATLAB calculate the values. Once the PID Tuner app loads, you can simply click the green arrow button to update your PID controller with the new values. Or you can use the response time and transient behavior sliders at the top of the window to adjust the tuned response. Then use the green arrow to update the PID constants. Once you are satisfied with the response, you can run the simulation. Note that you must click Apply at the bottom of the window after making any changes to the parameters. For this example, we are applying a harmonic force with a magnitude of 5 newtons and a frequency of 2 pi to both masses, and we are setting the desired position of the top mass to 3 centimeters. In the PID controller window, I am using the PID constants 1, 0, and 0. Make sure to click Apply on both the Block Parameters window and the PID controller window before running or updating the model. Now we can run the simulation. We can see that the PID constants we used are insufficient to keep the mass at its desired position of 3 centimeters. Before changing the constants and running a new simulation, we will save the position data of the controlled mass in the workspace to use later. All simulation data is saved within the out variable. For this module, the desired position, the simulated position of the controlled mass, the simulated position of the non-controlled mass, and the simulation time are saved. Any of these can be saved independently by saving them to a new variable, like so. Now I will use the PID Tuner app to calculate new PID constants, update the block, and run the simulation again. We can see that the new constants are much better at keeping the mass at the desired position. Now I will compare the controlled mass position data from the first simulation to the controlled mass position data from the new simulation. The second simulation in red reached the desired position very quickly, although there's still some oscillation about the line. This virtual lab helps students see the effect each constant of a PID controller has on a system by letting them run many experiments very quickly and allowing them to easily save and compare different systems. Thank you for watching.